Hello, and welcome to Empowered Learning. This particular video will be about finding zeros of polynomials of high degree. And what we mean by that is polynomials that have a degree or highest exponent of more than 2, so 3 and above. To be specific, our main goal here for this video is to show you all the tools and skills that you need to be able to factor down a polynomial of high degree, write that polynomial in its factored form, and then graph the polynomial. Towards the end of this video, we will also go over how to take the fact that if we know something about the zeros of a polynomial, but we don't know how to express that algebraically, how could we piece that information together to be able to come up with a factored form of that polynomial. In addition to that, multiply it out to see what it would actually look like in its standard canonical form. So the first thing that we'll talk about is the skill of synthetic division. And so we'll talk about that, see what it is, and we're going to also see how, by studying the remainder and the factor theorems, how we can actually use synthetic division to do more than just verify that a particular polynomial has a certain number that is a zero of it. And again, what we mean by a zero is a number that we can plug into our polynomial for x. And when we evaluate it, we get 0 as a result. We're also going to study the rational zeros theorem. And this is a very important theorem for what it is that we're trying to do. This theorem basically gives us a way to sort of jumpstart our process of taking a polynomial of high degree to start the process of factoring it down. And one of the things that we'll see is that we are going to use synthetic division to help us in that process. To speed up things, I'm actually going to use some technology as well to help you to be able to find what it is that we need to find from the rational zeros theorem quicker, so that we can apply our skills that we know to be able to get what it is that we want. So the Cardinal rule of signs, it is not necessary to know this particular rule. So if you are taking a pre-calculus course or college algebra course where you don't specifically study this, you can skip this part of the video. But what the Cardinal rule of signs basically does is give you a way of having a ballpark figure of the number of positive and negative zeros. And it actually helps out whenever we're doing applying the rational zeros theorem, because if you have a long list of possible zeros, because that's what the rational zeros theorem helps us to be able to know what are our possible zeros for a particular polynomial. The Cardinal rule of signs will say, out of all those, we have so many negative zeros, so many positive zeros. And if we know that from the rational zeros theorem, and we've tried a few out, that we only have, let's say, 1 negative zero, then once we find that 1, we know that we don't have to search for any more. And so, of course, that helps us to be able to cut down on the amount of work that we have to do. But that is essentially what the Cardinal rule of signs is about. We'll also talk about the types of zeros that we have. So in other words, we want to classify them so that we'll know whenever we say that a polynomial has a certain type of zero, whether it's rational, irrational, or complex, we'll know to whether expect that, hey, that's just a zero that kind of stands alone, or that particular zero is paired with another type of zero. And so that gets into what we call the irrational and complex conjugate pairs theorem. And this theorem essentially just states that if I know that a particular irrational number is a zero for a polynomial, then I know that its conjugate is also going to be a zero. Same thing for a complex number. If I have a complex number I can plug into a polynomial and the result ends up being 0, its conjugate also does that. And then finally, we will do some actual practice examples here. So this will kind of be the potpourri area where we'll take all the things that we've learned up into this complex conjugate pairs theorem and apply it to be able to factor down our polynomial of high degree and to be able to write it in factored form and graph it. Okay. And then of course, this will be, essentially another way of actually doing that. So the sketching graphs part. So we'll factor it down, then sketch a graph. So these two kind of go together. All right, so now that we have an introduction on what it is that we're actually trying to do, I'm going to go ahead and go straight into it. So the first thing here is synthetic division. So synthetic division is a special case of doing polynomial division. And essentially what we're doing is taking a polynomial that we call, in general, f of x, and we're going to divide it by a linear factor, x minus r. So to kind of give you an example of what this would look like, if f of x is going to be this particular polynomial here, then we're essentially going to divide this cubic polynomial by this linear. Okay. So one of the things that I want to stress here is that whenever we're doing synthetic division, it only applies to this type of polynomial division. So for instance, if I would have something like x squared plus 2, and I wanted to take that and divide it by x cubed minus x squared plus 2x plus 4, then synthetic division does not work for this. Okay, it only applies whenever we have a polynomial being divided by a linear expression here, meaning that the highest exponent on any variable is a 1. Okay, so the first thing that we're going to do here is look at regular polynomial division, study and see how that works, just in case you forgot. And then we're going to see how that polynomial division, when we do it normally, or what I call the long way here, we're going to see how does that actually translate over into synthetic division. Okay, so if we look here, you'll see that I have my polynomial f of x, which is a cubic function, and I am dividing it by x plus 2. Okay, and so we see with this whole process here that when we do that, we get a remainder of negative 12, and we know that we could rewrite f of x as just the divisor, which is this, times the quotient, because of course what's above the house here for division is the quotient, and then plus the remainder. So what I'm going to do now is actually break away from this for a second, and we're going to go through the process of doing the actual polynomial division here so that you'll understand clearly how we got this result, and then we'll come back to the notes here and then get into the synthetic division. All right, so we have rewritten our polynomial that we want to divide by x plus 2. And so to start this process, we essentially just ask ourselves for this first term here, x cubed, x goes into x cubed how many times? And of course, we see that x times x squared is going to give us x cubed. So we just put x squared here. So from here, what we do is we just go ahead and multiply x squared by both terms here, see what we get, and then we're going to subtract. Okay. Now, the reason why we're doing this is it's the same way that we do normal division. So for instance, let's say if I had 5 divided by 231. Okay. So here we know that 5 doesn't go into 2, but 5 does go into 23, and it goes into it 4 times. And then of course, 4 times 5 is 20. We'll subtract, get 3, and then we bring down the 1, and then we'll start that process again. 5 goes into 31 6 times, because 6 times 5 is 30. So 6 times 5 is 30. We subtract again. We have remainder 1. And since we have no numbers left, we can just say that that's the remainder 1. Just like how we did this, we're going to continue on here. So we say x squared times x is x cubed. X squared times 2 is a plus 2x squared. Okay. From here, what we have to do is subtract, just like how we did here. But notice that when we subtract, we're actually subtracting both terms. And so a simple way to think about this is that instead of saying we're going to subtract both terms, just change the sign on both terms. So what I'm going to do here is just erase. And since both of these terms were positive, what we'll do is just make them negative to apply the subtraction. From there, we know that these x cubes cancel to 0, and that negative 1x cubed plus a negative 1x squared plus a negative 2x squared is a negative 3x squared. From here, we bring down the plus 2x and we start the process over. So here we say x goes into negative 3x squared how many times? Or put another way, x times what gives me a negative 3x squared? Well, that's just going to be minus 3x here, because minus 3x times x will give me a negative 3x squared. So after that, we just repeat the process, figure out what we need, and then subtract. So negative 3x squared. So negative 3x times x gives us a negative 3x squared here. Negative 3x times a positive 2 gives us a negative 6x. And then, of course, to subtract, we would have to change the sign. And of course, the negative 3x squareds here will cancel to 0. And of course, 2x plus 6x is 8x. And then we bring down the plus 4 and we do the process again. We see here that x times 8 will give us 8x. So here we will put plus 8. And then we will continue on again, just like how we had before. So 8 times x will give us a positive 8x. And 8 times 2 will give us a positive 16. And since both of these terms are positive, we'll change the sign, make it negative. The 8x's cancel to 0. And then we have 4 minus 16, which is negative 12. And so we see how what we do here is the same thing that we get here. Okay. Now, what I've done over here is basically said that I can rewrite my polynomial divided by this by fact, this should be x plus 2 here. So don't know how that got to x minus 2, but that should be x plus 2. So I'll go ahead and correct that. So f of x divided by x plus 2 is the same as saying the quotient plus the remainder divided by the divisor. And again, this is nothing more than saying that I could rewrite 231 divided by 5 as 5 times 46. And then I have 1 out of 5 left. So if I looked at this, 231 divided by 5 is basically asking how many groups of 5 do I have in 231? Well, I have 46 groups of 5 in 231, and then I have 1 remaining, or 1 out of a group of a possible another 5 remaining. So that's essentially what we're saying here. So we could say let's see. We could say here that we know that this x cubed minus x squared plus 2x plus 4, all that divided by x plus 2 is just another way of saying I have x plus 2 groups of x squared minus 3x plus 8. And then I have negative 12 left over out of a possible another group of x plus 2. And of course, again, that looks very similar to what we have here. If I write it in this form, and what you see here is just me multiplying this equation here by x plus 2 on both sides. And that basically gets rid of the fraction. And so again, we see that the dividend is what is inside the division house. The divisor here is what is outside the house. The quotient is what is on top of the house. And the remainder is what's at the bottom of the house. Okay. Now, for what we just did, this doesn't necessarily, what we're doing here doesn't necessarily go with the whole concept of synthetic division, in that you should know this already, but I find that a lot of students don't know or don't remember how to do this, so that's why I cover it first. So now that we've gone over regular polynomial division, let's see how we could do this same thing using synthetic division. And we're going to see the similarities as well as the differences in between doing the synthetic division versus polynomial division the long way. So now we're going to do this polynomial division via synthetic division now. And remember that whenever we do synthetic division, we can only do this abbreviated step whenever we have a polynomial being divided by a linear factor here. Okay. So the first thing that we want to notice here is that if we say that x plus 2 is equal to x minus r, then what that tells us here is that our r in this case is going to be a negative 2. And so to make this real simple, if I have, let's say, x plus 2, then I know that the corresponding 0 for that is x equals negative 2. And essentially all you're doing is just saying, I'm going to set this equal to 0 and figure out what x is. Okay. So if x plus 2 is what we call your factor, then x equals negative 2 is going to be your 0. If I had something like x minus 3 is a factor of my polynomial, then if I set that equal to 0 here, then I know x equals 3 is the corresponding 0. Okay. So for our problem here, since we have x plus 2 as our factor, or what we're trying to divide our polynomial by in this case, if we set that equal to 0, then of course we get x is equal to negative 2. Now, the reason why I use the language of if x plus 2 is a factor here, or if x minus 3 is a factor here, is because we're going to see later on with the factor and remainder theorems, that is the language that's used in that. Okay. For right now, all we're doing is just saying, will this particular polynomial be divided by this linear expression here evenly? Meaning that, will we have a remainder or not? We already know that we will have a remainder, and that remainder is going to be negative 12, but we're just going to show you how we get that by using the abbreviated way of doing division for these types of problems here by doing synthetic division. So we see here that where we place our 0 is going to be here in this synthetic division setup. We're going to write all of our coefficients of our polynomial f of x in order. And so what I mean by in order is we write the coefficient for the x cubed, then for the x squared, then for the x, and then for the constant terms. Okay. One of the things I want you to remember, and I'm going to state this again, is that if we do not have, let's say, an x squared term here. So let's say this term was gone and we just had x cubed plus 2x plus 4. Then what we would put here is a 0 in its place. And so we must do that with synthetic division in order to get everything to work properly. So if we forget to do that, then everything that we come up with is going to be off. Another way of saying it'll be incorrect. Okay, so we need to make sure that we remember that. And I'll mention it a few more times just to make sure that you remember it. All right, so let's see if I can get rid of all of this. All right, so we see that we have all of our coefficients here. So we have the 1 for the x cubed, the -1 for the x squared, the 2 for the x, and the 4 for the constant terms. So to do synthetic division, all we do from here is whatever this first number is, we bring it down, and then we do a series of multiplying and adding. So we say -2 times a +1 is a -2, and then we add. So a -1 plus a -2 is a -3. Then we repeat the process. A -2 times a -3 gives us a +6, and we add. So 6 plus 2 is 8. And then we see a -2 times a +8 will give us a -16. And if we say 4 minus 16 or 4 plus a -16, then of course we get -12. And so notice here that we got our remainder of 12 just like we got here. Okay. Another thing that I want you to note is the following. Also notice that the understood 1 that is right here, the -3 that's right here, and the +8 that we have there also map back to this 1, this -3, and this +8 here. So what this is showing you is that the 1, -3, and 8 here actually represent our quotient, which would be 1x squared minus 3x plus 8. Okay. So what that's saying there in synthetic division form is the same exact thing that this is saying here. Okay, so now we see how, whenever we do synthetic division, how that translates over to what we're actually doing whenever we do long polynomial division. And so you see that doing the synthetic division is a much faster process than what we did here. All right, so let's go ahead and move on now. So in the notes that I have, if you're taking my course, I kind of go through this step by step, but you see that I've already kind of worked it out for you. So we're just going to skip all of this. All right, so now what we want to do is get some practice on doing synthetic division for these types of polynomials. The one thing that I want you to notice for both types of polynomials here is that we're missing some terms here. So for example A, we're missing an x to the 5th term, we're missing an x cubed term, and we're missing an x term. For example B, we're missing an x term. And so remember I told you before that whenever we are missing terms, we're going to put zeros in its place whenever we do the synthetic division. And that's why, again, I have that note here. So for example A, we're going to set up the synthetic division. Since this is x plus 3, we know that our value that we want to use to do the synthetic division here, which we're going to call a potential 0 at this point, is going to be -3, because that's what makes this expression x plus 3 go to 0. And then from here, we write all of our coefficients in order. So our x to the 6th coefficient is 2. We don't have an x to the 5 coefficient, so we put a 0 in its place. -18 is going to be our x to the 4th. 1, and then nothing for x cubed, so we put a 0. 1 for the x squared, nothing for the x, so we put a 0. And then we have -9 for our constant term. We make our remainder box here. And then the first step, we pull down the 2, and then we do a series of multiplying and adding. So -3 times a +2 is a -6, and then we add. Then we'll repeat again, -3 times -6, +18, then we add. -3 times 0 is 0, add. -3 times 0 is 0, 1 plus 0 is 1. -3 times a +1 is a -3, add. And then -3 times -3 is a +9, and we get 0. Okay. So we do the same thing with example B. Since our expression that we want to divide this particular polynomial by is x plus 3, then we're going to put -3 there again. We write our coefficients. -4 for the x cubed term, 5 for the x squared term. We don't have an x term, so we just put 0 in its place, and then we put an 8 for the constants term. And then again, draw a remainder box, pull down this number, and then multiply and add. So -3 times -4, +12, add. -3 times +17 is going to be a -51, and then we add. And then -3 times a -51, that would end up giving us +153, and then we add. So we see how to actually perform synthetic division on polynomials that don't necessarily have all of the terms present, based upon what the leading term of the polynomial is. All right, so one of the things that we want to address here is the fact of understanding what our synthetic division is trying to communicate to us. And so here we say, attention, if the remainder of our doing the division of f of x times x minus r is 0, which means we get a 0 in the remainder box, then we know that x minus r is going to be a factor of f of x, meaning that f of x can be rewritten as x minus r times something else. Okay. And another way of being able to say that is that f of x is divisible by x minus r. So give you a simple example of that. Let's say that I had x squared. I'll make it a little bit easier here. Just kind of make my point. So let's say here that I had x plus 3 times x minus 2. And if I divided that by x minus 2, then of course these two terms would reduce to 1, which just gives me this as a result. And so what you're seeing here is that whenever we take a function and divide it by something else and it's divisible by it, that means that we can divide it and we get no remainder. Hence why we ended up getting 0 in the remainder box. Now, if we look back at what we were doing earlier, we see that we get a 0 in the remainder box here, but we don't get 1 here. So what that's letting us know is that for our first polynomial in example A, we know that x plus 3 is actually a factor of this polynomial. Okay, the 2x raised to the 6 minus 18x to the 4th plus x squared minus 9. So we see that. We also see that x plus 3 is not a factor of this polynomial because we got a remainder of 161. Okay. So the point of asking these questions out here, it says from examples A and B above, which shows that x plus 3 is a factor of f of x. Well, that was example A. Okay. Now, we also see that because x plus 3 is a factor, that factor goes to 0 whenever x is equal to -3. So example A is also implying that x equals -3 is going to be a 0 of the polynomial that we have. So going back up here, what we are essentially seeing is that if x plus 3 is a factor, then if I was to take this particular polynomial, plug in -3 into it, the result that I get would be 0. Okay. Now, there's a few things that are kind of ironic about what I just said. One, we see that we have 0 in the remainder box. So one of the things that we're seeing is that I could figure out what my polynomial would end up being if I evaluated at a particular number here just by doing synthetic division. Okay. The other thing that I can see here is that if I know in this case that f of x can be written as x plus 3 times something else, because I know that x plus 3 is a factor of it because this holds true, then I also know what the something else is here. And if we look at our synthetic division, we took a polynomial of degree 6, we divided it by a polynomial of degree 1, which is what the linear expression is here. So 6 minus 1 gives us 5. So our quotient that's here is going to be x to the 5 for this one, x to the 4, x to the 3, x to the 2, x to the 1, and x to the 0, or a constant term. So this question mark here is actually 2x to the 5th minus 6x raised to the 4 plus x minus 3. So that is what this something else would be right here. All right, so now that we've actually gone over the basics of synthetic division, the next thing that we need to talk about are these theorems that help us to be able to get to the main thing that we're trying to do, which is take a polynomial, factor it down, write it in factored form, and then be able to graph it. And of course, part of the process of taking a polynomial of high degree and factoring it down is figuring out what its zeros are. And so these 4 theorems here are going to either directly or indirectly address the fact of trying to find the zeros for these polynomials of high degree. So we're going to first talk about the remainder theorem and the factor theorem. And so both of these theorems are like cousins of each other. And so they both kind of say the same thing, but they say it in a different way. So let's look at the remainder theorem first. So what the remainder theorem says is essentially what I just got through talking about a minute ago, which is if we let our function be a polynomial, and if we take our function and divide it by a linear factor here, then what we get in the remainder box is really the same thing as saying what is the value of our polynomial evaluated by this number r, or evaluated by what we would call our potential 0. Okay. And again, it's only potential because we're hoping that we would get 0 in the remainder box, but if we don't, that's fine. So in general, what we see is that synthetic division is another way of being able to evaluate a polynomial. Again, I'll go back just to make sure that I'll make this point crystallize here. So we see that for this particular polynomial that we had, we used -3 in our synthetic division, and we saw that we got 0. And remember, I told you that this was the same thing as saying that if I was to plug in -3 into x for each term of this polynomial, I would get 0 as a result. Okay. Similarly here, if I plugged in a -3 everywhere for x in this particular polynomial, what I would get is 161 as a result. Okay. So this particular theorem, the remainder theorem, just basically says, hey, there's another way for us to evaluate polynomials without us actually having to plug in the values of x and do all that computation. So as an example here, we see that if I was to plug in a -2 here, you can't really see that, but there should be a -2. The negative got kind of trapped into the equal sign there. But if x is -2, then here we see that when we evaluate that, we get a -12. But we also see when we do the synthetic division, we get the same thing, -12. So we see that f of -2 for this particular polynomial here ends up being -12. Now, the factor theorem states that if we know that f of x is a polynomial, and that if we plug in x into a particular function and the result ends up being 0, then we know by default that x minus r is a factor of that polynomial. And vice versa is also true. Okay? If x minus r is a factor of the polynomial, then we know that the corresponding value r is a 0 of the polynomial. Okay. Now, again, we've already showed that. So if we remember back in our previous example here, we knew that for the polynomial f of x in example A, that if we plugged in a -3, we would get 0 as a result. And that lets me know that x minus a -3, or put another way, x plus 3, is a factor of f of x. Okay. And remember, I'm talking about example A above here. I'll go back to it just to remind you. So I'm talking about this specific example here, okay? Because we saw that if we let -3 be x here, that we end up getting 0. And of course, our synthetic division shows us that in another way. So we also see here from the factor theorem that the opposite, or the converse statement, is also true, meaning that if I know that x plus 3 is a factor of some polynomial, then I know that if I plug in -3 into that polynomial, I'm going to get 0 as a result. So this is going to be what we call a bidirectional statement, or biconditional statement. Okay, so these two things together basically say that you can't have one without the other. So if I know that a particular value, if I plug it in for x to a function, if it's 0, then I know that x minus r has to be a factor. And if x minus r is a factor for a particular polynomial, then I know that whatever value that makes this go to 0, which is going to be r, actually makes the polynomial go to 0. Okay. All right, so next we're going to talk about a very important theorem called the rational zeros theorem. What this theorem does is says that if we have a polynomial that meets certain conditions, then we can come up with a list of possible zeros that might work for this polynomial, meaning that if the polynomial meets certain conditions, then that means that I can come up with a list of numbers to where if any of these numbers of a certain type end up being a 0 for the polynomial, meaning that I plug in that particular value and I get 0 as a result, it has to come from this list. Okay. So let's read the theorem, interpret what it's saying, and then see an example. So we see here that the rational zeros theorem says if we let f of x be some polynomial, and of course, all of this is just mathematical jargon to give you a polynomial in general, where this a sub n here is going to be the number or the coefficient for the leading term, which is the term that has the variable with the highest exponent. And of course, my a sub 0 is going to be the term that is the constant term for my polynomial, okay? So if we let our function here be a polynomial where all of my coefficients here are rational numbers, and that's a key thing. So in other words, a number that can be written as a fraction. If our polynomial meets this condition, then if, and this is key word, if our polynomial has any numbers that I can plug in for x that will make it go to 0, and those values are rational number types, meaning numbers that I can actually express as a fraction, then it has to come from, well, what I call this grab bag or a list of possibilities. And so how we get it is we essentially say, well, what are all the factors of our constant term here? And we're going to divide that by all factors of our leading term here. And when we do this, we're going to do all combinations thereof of these numbers. And so that produces our list. Once we have our list together, then we just try them out. And we're going to see that how we would actually try them out in an old school kind of way is we would use synthetic division. Now, since we have access to technology here to kind of speed up the process, when we do some examples, I'm going to use technology to kind of get you started. And we're only going to use synthetic division when absolutely necessary. Okay. Okay. Now, last thing I want to say before we get to the example here is that the rational zeros theorem does not guarantee that any of the numbers in the list that we get works. It's just saying that if we have zeros of this polynomial that look like rational numbers, then they're going to have to come from this list. Okay. No guarantees, but if we have one, it's got to be in the list. So let's see an example here. So we want to find all possible rational zeros for this particular polynomial. So we see it's a 5th degree polynomial, and we notice that our leading coefficient is 3, and our constant coefficient, or our last coefficient, is essentially it's negative 12, but we're going to ignore the minus sign there because, as you can see, we include plus or minus with all the factors. So when we talk about what are the factors of 12, it's just 1, 2, 3, 4, 6, and 12. And so we consider plus or minus because, we want to basically cover all cases here. We see that the leading coefficient is 3, and since 3 is prime, then its only factors are 1 and 3. And so we do all combinations thereof. So the way that I put this together is I said, let's hold negative 1 here, and then just divide 1 by 1, 2 by 1, 3 by 1, 4 by 1, 6 by 1, 12 by 1. And then from there, we get this and then do the same thing with the 3. Do 1 by 3, 2 by 3, 3 by 3, 4 by 3, 6 by 3, 12 by 3, okay? And any factor that we see repeat, we just ignore it, okay? Meaning that we don't have to have, for instance, we have a plus or minus 1 here. We see that plus or minus 3 over 3 also gives us a plus or minus 1. So I don't have to worry about this, okay? I already have it listed once, so I don't have to list it again. So same thing here, 6 divided by 3 is 2, 12 divided by 3 is 4. So all of the non-repeating factor combinations that we get left is what our list of possible zeros would be, okay? And so what this says is that if the polynomial that we originally started with had any numbers that I can plug in for x that would look like a rational number, that would make my polynomial go to 0, it has to be out of this list. Okay. Again, there is no guarantee that any of these numbers actually work for our polynomial. But if our polynomial has a rational number type of 0, meaning a number that can be written as a fraction that we can plug into our polynomial and it makes it go to 0, it has to be from this list. Okay. And so this is the theorem that we use to jumpstart our process of factoring down polynomials of high degree. So the next theorems that we're going to talk about will be the irrational conjugate pairs theorem and the complex conjugate pairs theorem. And this particular theorem is relatively easy. Just to kind of give you some insight here, for those of you that are actually following the notes, because you're taking a course from me that talks about this topic, you'll notice that I skipped the Descartes rule of signs, and that's because I'm going to make a separate video for that, just because whoever may be watching this, some instructors may teach it, some instructors may not. So again, I'll make a separate video of that and talk about that particular concept separately, because you may not need to know that to do what you're doing here. So the irrational conjugate pairs theorem essentially says this. So if we know that we have a function that's a polynomial, and let's say that we know that 2 minus square root of 5 is going to be a 0 for our polynomial f of x. Okay, then if we know that that's a 0, then we automatically know that 2 plus square root of 5, which is the conjugate of this particular expression here, meaning that everything is the same except for this sign. We switch it to a plus, and that's its conjugate. So our polynomial here, if it has this 0, then it also has to have this 0. And it comes in conjugate pairs. The same thing holds true for the complex conjugate pairs theorem. Let's say if we had a complex number 2 plus I that is a 0 for our polynomial f of x, then we know that 2 minus I also has to be a 0 for that. Now, the reason that that comes about is it actually comes from the quadratic formula here. So I'm going to break away here for a second and kind of show you why that is. So let's move forward, give ourselves some room here. If you remember with the quadratic formula is this. And of course, that goes along with quadratic equation of this form. Okay. Now, if you've already studied how to solve quadratic equations using the quadratic formula, one of the things that you've probably encountered here is cases when this particular expression that we call the discriminant ends up being negative. Okay. And so the discriminant, in general, what it does, it discriminates on or categorizes what these answers are going to look like to this equation. Now, specifically, whenever our discriminant ends up being negative, we have a situation like this. And I'm just going to make up something to kind of make my point, to keep from having to do so much symbolic theory here. So let's say if I have -1 plus square root of -4 here divided by 2. Okay, so let's say I have a quadratic equation that ends up being that. Well, we know here that the square root of -4 is actually an imaginary number. And what we would do is retranslate this as square root of 4 times square root of -1. And by definition, square root of -1 is I. And so we would rewrite this as -1 plus or minus square root of 4 is just 2. I, all that over 2. and then correct complex number form, this would look this way, okay? And so if you notice here, we have the plus or minus part here, which means that one of these is going to be 1/2 plus I. The other one is going to be negative 1/2 minus I. And whenever we have complex solutions to a quadratic equation, they're always going to come in conjugate pairs, okay? The same sort of thing happens if we had a situation where, let's say, our discriminant here is greater than 0, but it's not a perfect square. So again, let's say if we had something like this. So in this case, we see that our discriminant is greater than 0, which means we're going to get two real distinct numbers. But again, we have, if I rewrite this, we have two separate answers here, which is negative 1/2 plus 5 square root of 5 over 2, and I have negative 1/2 minus square root of 5 over 2. Okay, and so anytime we have zeros that are either complex or irrational, we know that they're going to come in conjugate pairs because of what we know from the quadratic form. And so because of that, that's why we have these two theorems here. Again, relatively simple to know. It's just, again, I would like for you to know where it comes from so that if you forget it, you'll know, hey, how do I remember what this is supposed to be? All right, so I'm going to conclude this particular video. My part 2 will be about the Cardinal's rule of signs specifically, and then we'll get into some of the examples. So for those of you that do not need to know the Cardinal's rule of signs, then you want to skip the part 2 portion of this video series that I'm going to do and move on to part 3.